capacitors behave in circuits is going to be a topic for the AP Physics 2 class, and a full treatment requires calculus, so obviously we're not going to do that. But you need to understand the basics of when you take one of these and you hook it up into a circuit, how is it going to behave? So the short version is, when you take a capacitor and you hook it up to any kind of voltage source, it's going to charge, and it's going to take some time to charge. It's going to charge up depending on its capacitance and depending on the resistor that any current has to travel through to get to the capacitor. It's going to take time to charge up. This is an exponential behavior, so the charging graph is going to do this, and discharging is going to do this if you disconnect it. And you need to know especially the boundary conditions of capacitors. When you take a capacitor and it has no charge on it at all, the moment you hook that up to the circuit, it acts essentially like a wire. It has no resistance. It allows charge to build up on either plate, which for our purposes means it allows current to flow through it. However, if you leave it plugged in for a very long period of time, then as the charge builds up and builds up and builds up, it develops a voltage that opposes the voltage that's charging it. So the more negative charge that piles up on the negative plate, the harder it is to put more there, vice versa on the positive side. And so a capacitor that is fully charged acts like an open switch or a broken wire. So to explore that a little further, let's look at two examples. We're going to look at a capacitor that is in series with a resistor, and then we're going to look at a capacitor that is in parallel with a resistor, and we'll use some light bulbs so that we can make it a little easier to see. Let's do it. So let's create a basic RC circuit with a switch, and we'll add another switch so we can bypass the battery. This is a short circuit and a bad idea, but for very short periods of time and a low voltage battery, not a big deal. So the question is, what is the current in the circuit the moment switch 1 is closed? Let's start by redrawing the circuit without the parts that don't matter at this time, and then realize at this moment the uncharged capacitor acts like a wire. Applying Ohm's law to this very easy circuit gives us I0 equals V over R. So what is the current a very long time later when the capacitor is fully charged? Well, a fully charged capacitor acts like an open switch. So the current has to be 0. And because brightness is determined by power, which is proportional to current squared, you should see the bright bulb get dimmer and go out as an exponential function, like this. Now that the capacitor is fully charged, what happens if we close switch 2 and bypass the battery? The capacitor now acts like a battery and provides voltage to the circuit, but its voltage decreases exponentially with time as it drains. This means the current starts as V over R and fades down to 0. Now let's take a look at our second circuit, where the capacitor is in parallel with one of the two bulbs. We have 3 separate currents in this problem, and we want to know what they are the moment the switch is closed. As before, let's redraw it without all the extraneous stuff. And remember, a discharged capacitor acts like a wire, and so it short circuits the second bulb. This makes the initial current in wires 1 and 3 V over R1, and the initial current in wire 2 0. A long time later, the capacitor acts like an open switch. So it's like that part of the circuit isn't even there. Applying Ohm's law here gives you I equals V over R1 plus R2 for wires 1 and 2, and I equals 0 for wire 3. Now that our capacitor is charged, we can close switch 2 and remove the battery from the circuit. Getting rid of the extraneous stuff gives us 2 resistors in parallel with a voltage source. Ohm's law gives us I equals V over R for both lamps, and the junction rule tells us that the current out of the capacitor has to be the sum of those. Finally, what are the currents a long time later? The capacitor is totally out of charge, so they're all 0. So there you have it. Capacitors in a circuit, if they are uncharged, for that split second, act like a wire. Capacitors that are fully charged in a circuit with a battery act like an open switch or a broken wire. Capacitors that are fully charged in a circuit that does not have a battery are going to provide the voltage and act like a battery. And after that split second at the beginning when you open or close a switch, it's going to transition exponentially from one state to another. See you next time.